Multiple grounding of neutrals in an electrical system with delta primary 480/277 volts, three-phase, 4-wire Y solidly grounded transformers associated with unit substations tied together with tie circuit breakers is not code compliant. The National Electrical Code, or NEC, dictates that a separately derived system must have a single point of grounding. Multiple grounding creates parallel ground return paths which can interfere with ground fault protection and increase the risk of electrical shock. Implementing partial differential ground fault protection schemes will not rectify the system's code non-compliance. While these schemes can detect and isolate ground faults, they do not resolve the fundamental issue of multiple grounding. The appropriate solution involves installing 4-pole main and tie circuit breakers to prevent multiple grounding of neutrals. 4-pole circuit breakers disconnect all 4 conductors, which are the 3 phases and the neutral, thereby isolating the neutral from other grounding sources. This ensures a single point of grounding, aligning the system with NEC requirements. The presence of multiple ground paths for neutral current can lead to several problems within an electrical system. Firstly, it compromises the effectiveness of ground fault protection devices. Ground fault protection relies on detecting an imbalance in current between the phase conductors and the neutral or grounding conductor. When multiple ground paths exist, a portion of the fault current may return to the source through these unintended paths. This reduces the current flowing through the designated ground fault return path, potentially preventing the ground fault protection device from tripping as quickly as required, or from tripping at all. Secondly, multiple grounding can create circulating currents within the grounding system. These circulating currents are caused by slight voltage differences between different grounding points. The circulating currents can lead to increased energy losses, elevated temperatures in the grounding conductors, and potentially create electromagnetic interference that can affect sensitive electronic equipment. Thirdly, multiple grounding increases the risk of electric shock. If a fault occurs, the presence of multiple ground paths can create voltage gradients in the earth surrounding the equipment. Anyone coming into contact with the earth near the faulted equipment may be exposed to a hazardous voltage. By ensuring a single point of grounding, the path of fault current is well defined and the risk of electric shock is minimized. Installing 4-pole circuit breakers is the recommended method for achieving a single point of grounding in systems with separately derived sources. Unlike 3-pole circuit breakers, which only disconnect the 3-phase conductors, 4-pole circuit breakers also disconnect the neutral conductor. This ensures that the neutral of each separately derived system is isolated from the neutrals of other systems when the circuit breaker is open. When the circuit breaker is closed, the neutrals are connected, and the system operates with a common neutral point. However, it is crucial that only one of the interconnected separately derived systems has its neutral bonded to ground. The other separately derived systems must have their neutral to ground connection removed to avoid multiple grounding. The NEC provides specific requirements for grounding separately derived systems. Section 250.30 outlines the requirements for grounding alternating current systems and specifies that a separately derived system must be grounded at a single point. This grounding connection must be made at the source of the separately derived system, such as the transformer. The grounding electrode conductor, which connects the system neutral to the grounding electrode, must be sized according to NEC Table 250.66, based on the size of the derived phase conductors. In addition to the single point of grounding requirement, the NEC also addresses the issue of ground fault protection. Section 230.95 requires ground fault protection for solidly grounded wire electrical services of more than 150 volts to ground but not exceeding 1000 volts phase to phase for each service disconnecting means rated 1000 amps or more. This requirement is intended to provide additional protection against ground faults, which can pose a significant fire and shock hazard. Ground fault protection devices are designed to detect relatively low-level ground faults and trip the circuit breaker or the disconnecting means to interrupt the flow of current. The NEC also specifies the maximum clearing time for ground fault protection devices. The clearing time must not exceed 1 second for ground faults that are greater than or equal to 3000 amps. This requirement is intended to minimize the duration of ground faults and reduce the potential for damage to equipment and injury to personnel. When installing ground fault protection, it is important to coordinate the settings of the ground fault protection devices with the settings of other overcurrent protection devices in the system. This coordination is necessary to ensure that the ground fault protection devices will trip before other overcurrent protection devices, such as fuses or circuit breakers, operate to clear the fault. Proper coordination of overcurrent protection devices helps to minimize the extent of the outage and prevent unnecessary damage to equipment. In addition to the requirements for grounding and ground fault protection, the NEC also includes requirements for bonding. Bonding is the process of connecting together all metal parts of the electrical system to create a lower impedance path for fault current. Bonding helps to ensure that all metal parts are at the same potential, which reduces the risk of electric shock. The NEC requires that all metal enclosures, raceways, and other non-current carrying metal parts of the electrical system be bonded together. The bonding conductors must be sized according to NEC Table 250.102. Based on the size of the largest ungrounded conductor. The NEC also includes requirements for equipment grounding conductors. Equipment grounding conductors are used to connect the metal enclosures of electrical equipment to the grounding system. This provides a path for fault current to return to the source in the event of a ground fault. The equipment grounding conductors must be sized according to NEC Table 250.122. Based on the size of the overcurrent protection device protecting the circuit. The NEC also includes requirements for grounding electrodes. Grounding electrodes are used to connect the grounding system to the earth. The grounding electrode system must consist of one or more grounding electrodes, such as a ground rod, ground plate, or underground metallic water pipe. The grounding electrode system must have a resistance to ground of 25 ohms or less. If the resistance to ground is greater than 25 ohms, an additional grounding electrode must be installed. The NEC also includes requirements for surge protection. Surge protection devices are used to protect electrical equipment from voltage surges, such as those caused by lightning strikes or switching operations. Surge protection devices are typically installed at the service entrance and other locations throughout the electrical system. The NEC requires that surge protection devices be listed and labeled for the intended application. The NEC also includes requirements for wiring methods. Wiring methods refer to the types of cables, raceways, and other materials that are used to install electrical wiring. The NEC specifies the allowable wiring methods for different applications based on factors such as the voltage, current, and environment. The NEC also includes requirements for conductor ampacity. Conductor ampacity refers to the maximum current that a conductor can carry continuously without exceeding its temperature rating. The NEC specifies the ampacity of different types of conductors based on factors such as the conductor size, insulation type, and ambient temperature. The NEC also includes requirements for overcurrent protection. Overcurrent protection devices, such as fuses and circuit breakers, are used to protect electrical circuits from overloads and short circuits. The NEC specifies the maximum allowable overcurrent protection for different types of circuits based on factors such as the conductor ampacity and the type of load. The NEC also includes requirements for equipment installation. The NEC specifies the requirements for installing different types of electrical equipment such as transformers, switchgear, and panel boards. These requirements are intended to ensure that the equipment is installed safely and in accordance with the manufacturer's instructions. The NEC also includes requirements for hazardous locations. Hazardous locations are areas where there is a risk of explosion or fire due to the presence of flammable gases, vapors, or dusts. The NEC specifies the requirements for electrical equipment and wiring in hazardous locations based on the type of hazard and the degree of risk. The NEC also includes requirements for healthcare facilities. Healthcare facilities have unique electrical requirements due to the need to provide reliable power to life support equipment and other critical systems. The NEC specifies the requirements for electrical systems in healthcare facilities based on the type of facility and the level of care provided. The NEC also includes requirements for emergency systems. Emergency systems are designed to provide power to critical loads, such as lighting, fire pumps, and elevators, during a power outage. The NEC specifies the requirements for emergency systems, based on the type of occupancy and the level of risk. The NEC also includes requirements for renewable energy systems. Renewable energy systems, such as solar photovoltaic systems and wind power systems, are becoming increasingly common. The NEC specifies the requirements for installing and operating renewable energy systems, based on the type of system and the applicable codes and standards. In summary, multiple grounding of neutrals is a code violation that can lead to several problems, including compromised ground fault protection, circulating currents, and increased risk of electric shock. Installing 4-pole circuit breakers is the correct solution to prevent multiple grounding of neutrals and ensure compliance with the NEC. By following the NEC requirements for grounding, bonding, overcurrent protection, and other aspects of the electrical system, it is possible to create a safe and reliable electrical system that protects people and property from electrical hazards. It's important to consult with a qualified electrical engineer or contractor to ensure that the electrical system is designed and installed in accordance with all applicable codes and standards. The correct application of the National Electrical Code is a critical step in ensuring a safe electrical installation. Firstly, identify the type of system you are working with. Is it a separately derived system, a service, or a feeder? Each has different grounding requirements. Secondly, determine the voltage and current levels of the system. This will dictate the size of conductors, overcurrent protection, and grounding electrodes. Thirdly, consider the environmental conditions. Is the system located in a wet, damp, or corrosive environment? This will affect the choice of wiring methods and equipment. Fourthly, ensure that all equipment is listed and labeled for its intended use. This ensures that the equipment has been tested and certified to meet safety standards. Fifthly, follow the manufacturer's instructions for installation and maintenance. This will help to ensure that the equipment is installed correctly and operates safely. Sixthly, verify that all grounding and bonding connections are properly made. This is essential for providing a low impedance path for fault current. Seventhly, test the electrical system after installation to ensure that it is operating correctly. This includes testing the ground fault protection, overcurrent protection, and insulation resistance. Eighthly, document all aspects of the electrical system. This includes the design, installation, testing, and maintenance. This documentation will be helpful for future troubleshooting and maintenance. Ninthly, keep the electrical system clean and free of debris. This will help to prevent overheating and other problems. Tenthly, train personnel on the proper operation and maintenance of the electrical system. This will help to ensure that the system is operated safely and efficiently. Multiple grounding is a dangerous condition because it creates parallel paths for fault current. These parallel paths can reduce the amount of current flowing through the intended ground fault return path, which can prevent the ground fault protection device from tripping. In addition, multiple grounding can create circulating currents, which can lead to increased energy losses and elevated temperatures. To prevent multiple grounding, it is important to ensure that each separately derived system has a single point of grounding. This can be achieved by installing 4-pole circuit breakers, which disconnect all 4 conductors, including the neutral. 4-pole circuit breakers provide a positive means of isolating the neutral from other grounding sources. When the circuit breaker is open, the neutral is isolated, and when the circuit breaker is closed, the neutrals are connected. However, it is important to ensure that only one of the interconnected separately derived systems has its neutral bonded to ground. The other separately derived systems must have their neutral to ground connection removed to avoid multiple grounding. The NEC provides specific requirements for grounding separately derived systems. Section 250.30 outlines the requirements for grounding alternating current systems and specifies that a separately derived system must be grounded at a single point. This grounding connection must be made at the source of the separately derived system, such as the transformer. The grounding electrode conductor, which connects the system neutral to the grounding electrode, must be sized according to NEC Table 250.66, based on the size of the derived phase conductors. In addition to the single point of grounding requirement, the NEC also addresses the issue of ground fault protection. Section 230.95 requires ground fault protection for solidly grounded wire electrical services of more than 150 volts to ground, but not exceeding 1000 volts phase to phase for each service disconnecting means rated 1000 amps or more. This requirement is intended to provide additional protection against ground faults, which can pose a significant fire and shock hazard. Ground fault protection devices are designed to detect relatively low-level ground faults and trip the circuit breaker or other disconnecting means to interrupt the flow of current. When installing ground fault protection, it is important to coordinate the settings of the ground fault protection devices with the settings of other overcurrent protection devices in the system. This coordination is necessary to ensure that the ground fault protection devices will trip before other overcurrent protection devices, such as fuses or circuit breakers, operate to clear the fault. Proper coordination of overcurrent protection devices helps to minimize the extent of the outage and prevent unnecessary damage to equipment.